Hello everybody. In this video we are going to discuss the second method that we can use to calculate the heat of reaction or the standard heat of reaction, which is using the heats of formation of reactants and products. But before we start, we need to understand first what we mean by the term the heat of formation. To understand this, we need to understand another term first, which is called a formation reaction. So there are some reactions that we can call formation reactions. So formation reaction of a compound, it is the reaction in which a compound is formed from its elemental constituents. This is what makes it a formation reaction, that it's formed from the elemental constituents as they normally occur in nature. So this is an important thing because we can have reactions that produce a compound using other compounds. But in the case of formation reaction, we are calling the reaction a formation reaction when the compound is formed from the reaction of elemental constituents. This is what makes it a formation reaction. For example, if I am talking about the reaction to form ammonium nitrate is NH4NO3 from its elements. So if I know that the enthalpy associated with forming 1 gram mole of crystalline ammonium nitrate from its elements is 365.15. I can write this formation reaction as this. It's nitrogen gas plus hydrogen gas plus oxygen gas produce ammonium nitrate. This is the heat of reaction. This is a reaction, so it has there is delta HR, there is enthalpy change due to the reaction. But when this enthalpy change due to the reaction or when this reaction is a reaction of the elemental constituents, when I say this, I don't mean that they are elements, necessarily elements. It is the simplest form of the element or the compound. So for oxygen, for nitrogen, for hydrogen, the simplest form which is available in nature is gases: hydrogen gas, nitrogen gas, and oxygen gas. So that's why I'm using these as the simplest form as it normally occurs in nature. So the enthalpy change associated with the formation of 1 mole of compound, which is ammonium nitrate, at the reference temperature and pressure, and this is important, and we will know shortly why at reference temperature and pressure, or at standard temperature and pressure. It's called the standard heat of formation. When I have the standard conditions of temperature and pressure, the heat of formation that we calculate here, it's called the standard heat of formation. And we give it the same symbol as we do for the heat of reaction. So the same heat of reaction, or this heat of reaction, is the same as the heat of formation. I can say this in this case because what I have in the left hand side of the equation are the elemental constituents, or the simplest form of the components. So where can I get these heats of formation? They are available in tables. We already discussed table B1 many times before. We have already covered big part of it. We covered the specific gravity, the melting point, the latent heat of fusion or melting, the boiling point, the latent heat of vaporization, critical temperature and pressure. But here we have last two columns. One of them is the heat of formation, the standard heat of formation, which is given the symbol delta HF. Node, of course, because this is the heat of formation. And as you see, it is exactly, we deal with it the same way we deal with the latent heats. You just find the compound, and from the compound you can find the latent heat, and you can find the enthalpy of formation. We said that the latent heat was calculated at or measured at the boiling point, which is available in the previous column. But the heat of formation is measured at standard conditions. So this is at 25 Celsius and 1 atmosphere. And this is very, very, very important. And we will come to this shortly in one of the examples that we will solve. But you need to keep this in mind, that it is always at the standard conditions. Here it was at different temperatures. Here it's at the same temperature for all the values that we have in the table. We said that there are the formation reaction is the reaction that is producing the compound from its elemental components, or the simplest compounds that can be available in nature. For these simple compounds, or the elements, the heats of formation of them are zero. Why? Because we don't form them. They're already available. We don't do any effort or put any energy to form these compounds. So this is, I collected some of the elements and simple compounds. We have hydrogen H2, N2, and O2. And for the elements like nickel, like iron, like lead, all of them have zero heat of formation. It doesn't matter if it's solid, if it's gas, the heat of formation of all of them is zero. So this is a good thing to know. So now, after we knew the heat of formation and we understood what it means, how can we use this heat of formation to calculate the heat of reaction? To do this, we use a very simple formula. And this formula says that if nu I, which is the stoichiometric coefficient of species I, of course it's positive for products and negative for reactants. This is something we know long time ago, and the latent heat or the heat of formation is the standard heat of formation of this species. We can calculate the heat of reaction using this formula. The standard heat of reaction, keep in mind that this is standard, and we said standard because it's at the same temperature or standard temperature and pressure, is equal to the summation of the stoichiometric coefficients multiplied by the standard heat of formation. We can rewrite this as the heat of formation of products multiplied by the absolute value of their coefficients plus minus the heat of formation of reactants multiplied by their stoichiometric coefficient. So it's very simple calculation, just addition and subtraction. We find what is the latent the heat of formation. We know the stoichiometric coefficients, and this is all. We just multiply and add. So this is a very simple and easy way of doing this. So there is one other point that I mentioned, that this is this law that we see here is an indirect application of Hess law. And to understand this, let's take this example. Let's say we have a reaction for calcium carbonate, heat of or the formation reaction of calcium carbonate. It's calcium plus carbon plus 3/2 oxygen produces calcium carbonate. And we have the formation reaction of calcium oxide. It is calcium plus half oxygen produces calcium oxide. And we know the heats of formation from the table. They are already tabulated. I didn't get anything from myself. They're already tabulated. I got the numbers from the table for the heat of formation of calcium carbonate, for calcium oxide, and for carbon dioxide, which is this number. And from this we can get the decomposition reaction of calcium carbonate, which is calcium carbonate decomposes by heat to form calcium oxide and carbon dioxide. So this heat of reaction can be, I'm looking at them now as normal reactions, okay, as just normal reactions. And these normal reactions can be considered, or we can apply Hess law to these reactions. So we can get equation 1 plus equation 2 minus 2 plus 3 minus 1, which is reaction 4 is negative reaction 1 plus reaction 2 plus reaction 3. And if we do this, we will get calcium carbonate to the other side, calcium plus carbon plus oxygen to the other side, and the rest is what we have in the right hand side, the rest is what we have in the left hand side. You'll see that with the oxygen will cancel out. We have 1.5, they will cancel. We have calcium will cancel out, carbon will cancel out, and we will end up with calcium carbonate produces calcium oxide plus carbon dioxide. So this is the heat of reaction. It is the same as Hess law. It's negative heat of first reaction plus heat of second reaction plus heat of third reaction. And the heat of the reactions is the heat of formation. So I can apply this to replace this delta HR by the heat of formation. So it's going to be -1 multiplied by the heat of formation of calcium carbonate plus +1 multiplied by the heat of formation of calcium oxide plus +1 multiplied by the heat of formation of carbon dioxide. What we have in brackets are actually the stoichiometric coefficients. So it's going to be the sum of the stoichiometric coefficients multiplied by the standard heat of formation. So this is Hess law, and what we have is Hess law used in an indirect way. So this is a very nice way of calculating the standard heat of reaction, which is very easy, very straightforward, and simple in calculations. So for this example that we have here, we want to determine the standard heat of reaction from the combustion of liquid pentane, assuming that water is liquid in the combustion product. So the combustion of pentane is C5H12. It's already in the table. So we can write the combustion equation, C5H12, which is liquid, and I put it liquid because the boiling point is 36, and the standard heat of reaction is at 25 degrees Celsius. It's standard. So at 25 Celsius, pentane is liquid. So this is liquid pentane plus oxygen produces carbon dioxide and water, and this is, it's important now to balance the equation properly because the heat of reaction is calculated using the stoichiometric coefficient. So if you want to calculate the standard heat of reaction, it is called, it's going to be calculated as follows. We have -1 multiplied by the heat of formation of liquid pentane, which is this, plus -8, which is the coefficient of oxygen. And without looking in the table, we know oxygen is the simplest form of the compound, so it's going to be 0, plus the coefficient of carbon dioxide, which is +5, multiplied by the heat of formation of carbon dioxide, which is gas, so it's going to be -393. I knew it's gas because it is it sublimates at -78, so it's gas at temperature more than -78. So we already saw a video about this before for the solid ice or the dry ice sublimation, and we know carbon dioxide at standard conditions is definitely gas. And for water, it is liquid. Of course, it's liquid because it boils at 100, so it will be liquid at 25 and 1 atmosphere. So we were using the liquid water heat of formation, and from this we can calculate the standard heat of reaction. Okay. One more example, which is going to be very, very useful here. If I do the heat of reaction with two different conditions, once where water is liquid and once where water is gas. So the heats of formation or the difference between the heat of reaction would be the difference of the heats of formation. And we solved an example like this before. And we said that the difference between these two is going to be the latent heat. This is something that we mentioned before. So we expect that the difference between these two numbers is going to be the latent heat of vaporization of water, which is this. But if we look at the numbers, you would notice that the difference between these two numbers, let me zoom in, the difference between these two numbers is not 40. The difference is almost 44, while the latent heat of vaporization is 40.7 almost, which is somehow strange, but actually it's not. And the reason is already here. This is the latent heat of vaporization at the boiling point. But this is the heat of formation at 25 degrees Celsius. So it's because of the heat of formation is not equal to the heat of formation of vapor is not equal to the liquid heat of formation plus the latent heat of vaporization in the table, because the latent heat is at boiling point and the heat of formation is at 25. So the difference is the latent heat of vaporization, but at 25 degrees Celsius, while this is the latent heat of vaporization at 100 degrees Celsius. So this is the reason why the two values are not the same. To clarify this more and make it easy for you to imagine, this is the latent heat of vaporization of water from the steam table, and of course I converted the units from kilojoules per kilogram into kilojoules per mole. And you would see here that the value changes with the temperature from 0 up to 120. And as it increases, the temperature increases, the latent heat decreases. What we have here is at 100 degrees Celsius. So if you see at 100 degrees Celsius, it is between 40 and 41, closer to 41, which is 40.66 or 40.7. While at the standard condition, which is 25, it's going to be 44, almost 44. So this explains why there is a difference in the values of the latent heat, between the latent heat and the difference of the enthalpy of formation of liquid and gas phases. So this is all what I want to discuss here. Next video, inshallah, we will talk about the third method, which is very, very, very similar to the heat of formation method, and we will discuss this and next time, inshallah. So let's see you then. Goodbye.